We'll now begin section 7.3, where we will discuss product sum identities. We're going to begin with the class of identity that contains an argument where the given trigonometric function is twice an angle. These are called our double angle identities. You can see that we have a formula for the sine double angle identity. We have three versions of a formula for a cosine double angle identity, and we have a tangent double angle identity. So again, the thing that makes it a double angle identity is right here. This 2u indicates that our argument is twice the angle. We see that as well on the cosine one and as well on the tangent. So for each of those formulas, what we're taking the sine, cosine, or tangent of is 2 times an angle. Therefore, we call them the double angle identities. Let's look at how these work with an example. Our example says, given that cosine x is equal to negative 2 divided by the square root of 5, and that sine x is positive, we want to find cosine 2x, sine 2x, and tangent 2x. So we want to begin by drawing a picture. We're going to place an angle in one of the 4 quadrants. The difficult part about the problem is that we have to decide which quadrant the angle should be placed in. We have 2 hints that are given to us in the problem. The first thing that we can look at is the fact that cosine is equal to a negative value. We know that that only happens in certain quadrants. Remember that your cosine is positive in the first and fourth quadrant and negative in the second and third. So we know right now that that angle is going to have to lie in either quadrant 2 or quadrant 3 because it is negative. The other information that we have that's going to be helpful is the fact that they tell us that sine is positive. So we know that that only happens in certain quadrants. We know that sine is positive in the first and second, and negative in the third and fourth. And so since it is positive, we know that we are dealing with either quadrant 1 or quadrant 2. And when we work the problem, we need to select a quadrant that meets both criteria. Therefore, the angle must be in quadrant 2. So I'm going to begin by drawing myself a picture and placing that angle in quadrant 2. So I'm going to put the angle in standard position, and the terminal side will be somewhere in quadrant 2. Now I'm going to make a triangle out of this angle. So technically the angle that we're looking at, angle X, is here, but we're going to use the reference angle, which we know will have the same values, and so we're going to place that here. Just for the sake of making it easy, I'm going to go ahead and call this X as well. And I'm going to drop a line down, forming my right triangle. Now, what do we know about the sides of that triangle? Well, our SOHCAHTOA definition tells us that cosine is the adjacent side over the hypotenuse. So we know that the adjacent is 2, and the hypotenuse is the square root of 5. Now, furthermore, we know that as we leave the origin and we trace out the edges of this triangle, we know that we're moving back in a negative direction on this 2. So I'm going to go ahead and place that negative on the 2. Then we can use Pythagorean theorem to find the missing side. So let's call this missing side B, and let's figure out what it is. So I'm going to say negative 2 squared plus B squared is equal to the square root of 5 squared. So negative 2 times negative 2 is 4. And the square root of 5 squared is just going to be 5. We'll subtract 4 from both sides, getting b squared is equal to 1, which implies, by taking the square root of both sides, that b is equal to 1. So now, if we're ready to find our double angle identities, we should have the information that we need. So let's begin with cosine 2x. Now, keep in mind that we have 3 versions of the formula for a double angle on a cosine. So I'm going to go back and look. I can either use cosine squared minus sine squared, I can use 2 cosine squared minus 1, or I can use 1 minus 2 sine squared. And it is completely up to you as far as what version of the formula you would like to use. I'm going to go ahead and use the first one. So cosine squared minus sine squared. So I'm going to write my formula down. And I'm going to use my triangle to determine my values. So cosine x is adjacent over the hypotenuse. Remember that we have to square it. Sine x is opposite over the hypotenuse. And that also needs to be squared. So squaring my first fraction, negative 2 squared becomes positive 4. The square root of 5 squared becomes 5. The 1 squared becomes 1. And the square root of 5 squared becomes 5. And so we end up with 4 minus 1 is 3/5 for our answer. Okay, so next let's do the double angle for sine. We only have one formula for double angle of sine, and that formula says 2 sine cosine. So I'll write my formula down, and I'll use my triangle to determine the values. So sine, remember, again, is opposite, which is 1, over the hypotenuse. Cosine is adjacent, which will be negative 2 over the hypotenuse. So we multiply 2 times 1 times negative 2. That gives me negative 4. And on the bottom, square root of 5 times square root of 5 is going to just give me 5. And for the third one, we want to find tangent 2x. And so we have one formula for that. Our formula looks like 2 tangent u divided by 1 minus tangent squared u. So let's write our formula down. 2 tangent x over 1 minus tangent squared x. Now when I look at my triangle and I determine the tangent, tangent is opposite over adjacent, so we're going to have 1 over negative 2. And we're going to be plugging that same value into the bottom for tangent and then squaring it. So on the top, 2 times negative 1/2, the 2's will cancel, leaving me a negative 1. On the bottom, I'm going to have 1 minus, and I'm going to go ahead and square the 1/2. That will become 1/4. So I have negative 1 divided by 1 minus 1/4 is going to be 3/4. And remember that when you have a number divided by a fraction, you're going to write the number down as is. You're going to take the reciprocal of the denominator and multiply. And so our final answer will be negative 4 divided by 3. Now, we can also use these double angle formulas for other types of problems. So we want to look at a few other examples. We can use the double angle identities to prove other trig identities, which is what we're seeing here. It says prove that sine 3x is equal to 3 sine x minus 4 sine cubed x. So what we're going to do is we're going to start with the left-hand side of this expression. And we're going to try to write it in terms of the right-hand side. Now, one trick that we have, especially as we get into higher powers on the argument, like 3x or 4x or 5x, higher coefficients, I should say, is to break that up into groups of 2, because we know that we do have formulas for the double. In other words, I'm going to write this 3x as 2x plus x. All right, and again, the reason why is because I know I have a formula for sine 2x, and sine x by itself shouldn't necessarily be a problem. So I can deal with those two separately easier than I can deal with a sine 3x. Now, this is a sum identity for the sine. So recall that we have a formula for that. All right, recall that our formula, and we learned this in the last section, our formula looks like sine of the first angle times cosine of the second angle plus cosine of the first angle and sine of the second angle. So remember that this is your sum and difference formula that we learned in the last section. Now, even further than that, we now have formulas to plug in for sine 2x and formulas to plug in for cosine 2x. So let's go ahead and apply those as well. So our formula for sine 2x is 2 sine cosine. Okay, and then we still have this cosine that I'm going to bring down. Okay, now I need a formula for cosine 2x. And remember that this formula, we have some options. Since there's already a sine in this term, I'm going to look for the version of the formula that has only sines in it. So I'm going to use this third version, the 1 minus 2 sine squared. And I'm going to plug that in for cosine 2 theta. Okay, and again, I'm doing that because I know that my last term up here only has sines in it. So I want to use something to plug in that's going to increase the number of sines and not add a cosine into that equation that I want to have to get rid of later. Okay, so let's look at what's left here. We have 2 sine, and we have 2 of the cosines, so I'm going to do cosine squared x. I'm going to go ahead and distribute this sine through this parenthesis. So sine times 1 is going to be sine. And sine times negative 2 sine squared is going to be negative 2 sine cubed. And we can see that cubed coming into play now that we need in the right-hand side. Now remember that we have an identity that we can use for cosine squared. Again, my issue is that in the right-hand side of the original problem, I don't have any cosines. So I need to figure out how to get rid of those cosines. So I do know that I have this identity, sine squared plus cosine squared is equal to 1. And we've seen how in previous problems how we can adjust this, like for example, subtracting the sine squared from both sides, to give us something that we can plug in. So cosine squared x will equal 1 minus sine squared x. And so I'm going to come back to my problem, and in place of this cosine squared, I'm going to put in 1 minus sine squared. And I'm going to leave the rest of it as is. All right, let's distribute. So I'm going to distribute the 2 sine x times 1 and the 2 sine x times the negative sine squared. So that's going to make negative 2 sine cubed x. And if we'll combine like terms, I think we are almost done. So we have a 2 sine and we have a 1 sine, which together makes 3 sine x. So that takes care of those two terms. And then we have a negative 2 sine cubed and a negative 2 sine cubed, which adding those together will make a negative 4 sine cube of x. And that is what we wanted to end up with for this problem. Okay, also in this section, they're going to introduce what are called power-reducing identities. All right, so we have a formula for sine, for cosine, and for tangent, and the purpose of having these identities allows us to take a squared term in a problem and reduce it where it will not have a squared anymore. Okay, so just what it says, reducing the power. Now, these identities follow quickly from the double angle identities. So you could take your double angle identities and see very easily how they come up with these power reducing identities. All right, let's look though at how they're used. All right, so our problem says express sine to the 5th power in terms of containing only first powers of sines and cosines. So we want to take sine x to the 5th, and we want to write it with sines and cosines, but with no exponents other than 1. All right, so what we're going to do is we're going to take that sine to the 5th, and we're going to break it up just like we saw in the last example. So I am going to make it a sine squared times another sine squared times a sine. Now I still have 5 of them, but in grouping them this way, I have formulas for the sine squared, and the sine x by itself should be something that I can work with. All right, so the first thing I'm going to do is I'm going to come back to my power reducing identities, and I'm going to take the sine one and plug it in for my sine squareds. So these are 1 minus cosine 2x over 2. So I'm going to put that here. I'm going to put it again for the second sine squared. And then I'm going to keep my sine x on the end. Okay, so I'm going to go ahead now and multiply these two parentheses together, which is going to indicate the need for me to do FOIL method. So let's do that first. So first times first will be 1 times 1. My outside terms will be 1 times negative cosine squared, 1 times negative cosine 2x, which will be negative cosine 2x. My inside terms will be negative cosine 2x times 1, which is going to give me another cosine 2x. And my last terms, cosine 2x times cosine 2x, is going to give me cosine squared 2x. On the bottom, we're going to have 2 times 2, which is 4. And all of that is going to be multiplied by this sine x that sits on the outside. Okay, so let's go ahead and combine those middle terms. So that is going to give me 1 minus 2 cosine 2x And then what I'm going to do is I'm going to take this 1/4, which is sitting as a denominator here, and I'm going to pull that to the front. And so I'm just going to go ahead and instead of rewriting this, I'm going to just take this and I'm going to move it out to the front. For my next step, I'm going to go ahead and distribute the sign through the parentheses so that I can get rid of that parenthesis. So I'm going to have 1/4 staying on the outside, and I'm going to multiply sine times each of these three terms. So sine x times 1 is just going to be sine x. Sine x times 2 cosine 2x is going to be 2 sine x cosine 2x. And then the last term is going to be sine x times cosine squared 2x. So now we're going to move to a new slide, and I'm just going to rewrite where we left off right here on our next slide, and we're going to continue. Okay, so the next step is a little bit tricky, so we want to be careful with this. What we want to do is we want to look at this part of our expression, because remember, we're trying to write it so that we don't have any powers bigger than 1. So that is really the only issue that we have left, is we have a cosine squared 2x. And I'm going to use this power reducing formula at the bottom. But the problem is, or the difference is, when I compare what I have up here to what I have down here, note that I have a 2x up here and just an x here. Okay, so what needs to happen is I'm going to come down here and I'm going to replace this x with a 2x so that it matches what I'm looking for. And if I do that, if I replace this x with a 2x, I also need to replace that x with a 2x. And so my problem then becomes, or my formula becomes 1 plus cosine 2 times 2 is 4x over 2. Okay? And so we're going to use that and plug that into our expression up here, finish up our simplifying, and hopefully at that point we'll be done. So I'm writing everything exactly as it is. And when I come to this cosine squared 2x, I'm going to substitute in my power reducing formula. I'm going to go ahead and distribute my sign across that fraction. So it becomes sine times 1, which is sine x, and then it becomes sine times cosine 4x. And both of these are over 2. Now, actually, what I'm going to do is I am going to break that fraction up so that each of those terms is over 2, because that will just allow me to simplify a little bit easier. So I'm going to put the sine x over 2 and then this larger term over 2. Okay, so the only other thing that we can do is combine like terms, and it's almost difficult to see your like terms, but you do have a sine x, which has a 1 sitting in the front of it, and you have a sine x here that has a 1/2 sitting in front of it. So we can add those two terms together. 1 and 1/2 make 3/2. So we have 3/2 sine x, and that's going to take care of those two terms. And then the other terms are going to stay as they are. And so with that, we have then done what they've asked us to do. We have reduced this so that we do not have any powers bigger than 1. And we have done the simplifying that is easy enough to do to get it in the most simplified form.